So I'd like to thank the organizers for inviting me. I'm going to talk about some recent joint work with Mike Lesnick on the stability of two-parameter persistent homology. And the goal of this work is to provide theoretical justification for the use of 2D persistent homology of certain density-sensitive bifiltrations as robust invariants of point cloud data. And what I mean by a robust invariant is something that's insensitive to outliers. And I'll say a little bit more about this in just a bit. But to give some context for this, I want to review the stability theorem for one-dimensional persistent homology, which is arguably one of the sort of cornerstones of the subject that justifies its use in analyzing data. And this theorem is originally due to Cohen, Steiner, Edelsbrunner, and Harrer. In the form I'm going to state it, maybe it's due to Chazal, Cohen, Steiner, Guibas, Mamoli, and Udo. And what it says is that if you have 2 point clouds, 2 finite metric spaces x and y, then the Gromov-Hausdorff distance between x and y as metric spaces provides an upper bound on the bottleneck or the matching distance between the persistent homology barcodes you get from the Vietoris-Rips filtration on the data. So for a standard way of associating filtered simplicial complexes to the data, there's a bound on the distance between the barcodes in terms of purely metric comparisons. And just to give you a very quick refresher, if you aren't intimately familiar with this, so if you have metric spaces here, x and y, then the Gromov-Hausdorff distance measures if you're allowed to move them around and superimpose them on top of one another, and then it looks for the sort of the worst discrepancy between matched points. So those blue circles indicate the sort of furthest apart points after I've moved those on top of each other. And here, the stability theorem tells you that the resulting difference between the barcodes, which in both of these cases, sort of in one dimension, have one long bar corresponding to the cycle that goes around the circle. The distance between those, when you match the bars optimally, is bounded by that metric distance. Okay, so this is great. This says if you take your data and you perturb it, by adding a little bit of noise around the data points or something like that in an ambient space you sampled from, that the barcode doesn't change that much. But it doesn't provide any guarantees at all about outliers or adversarial noise. And in fact, it's easy to see that persistent homology of the Vietoris-Rips complex is not robust to outliers at all. And there's, Shmuel Weinberger is as fond of talking about tiny handle bodies at infinity. And that captures the kind of thing that happens where I can add some adversarially chosen complicated topological features very far from the core of the data that use a small number of points. Think about minimal complexes for circles and spheres. Okay, so what do you do? People are aware of this problem, and there have been a variety of approaches that incorporate density. And just to discuss 3 representative ones, so Chazal, Cohen, Steiner, and Marigot introduced something called a distance to a measure filtration. Phillips, Wang, and Zheng studied kernel distance filtrations. Both of these use a sort of a width or a smoothing parameter to smooth a little bit to control the influence of outliers. A slightly different approach I worked on with Gal, Mandel, and Pancia to use a look at distributions of barcodes you get by looking at subsamples of your data. In all of these cases, you're doing the thing that people always do to deal with outliers, namely you're trying to smooth them away or sample them away. And all of these require parameter choices that encode information about some local feature scale, either the width of the kernel or the width, the width parameter and the distance to a measure filtration, or the sampling rate for this barcode distributions approach. And there are other ways you could do this too, all of which have a similar flavor. But instead, I want to talk about a different way to think about it, which is to use bifiltrations in 2-dimensional persistent homology. And so in some sense, multidimensional persistent homology was introduced by Carlson and Zamaroni for just this reason, where the idea is now you have one direction that encodes metric information, which is what you normally have in one-dimensional persistent homology, the other direction encodes some kind of density parameter. So, as you go out in the filtration, you both vary the density you're looking at and the feature scale. And so now we're working with metric measure spaces, x dx mu x, where mu x now is a density, is some measure with respect to the, Borel structure on x. And here, so you can now introduce, we're going to study some parameter-free density filtrations. And so, sort of a canonical one was written down by Chazal, Cohen, Steiner, and Marigot. And this is maybe what you call the measure bifiltration, where the bifiltration of x at parameters k and r is given by the points in x, such that if you take the measure of a ball of radius r around x, that's greater than or equal to k. And the particularly interesting case for finite metric spaces is when you take the measure to be the normalized counting measure. So where the mass of a point is 1 over the number of points, basically. It's easier to work with a combinatorial version of this. And for this, we use the idea of the barycentric subdivision of a simplicial complex. So there's a picture there of a triangle that's been barycentrically subdivided, where we've cut it into 6 smaller triangles. And combinatorially, if you have a simplicial complex S, then the k simplices of the barycentric subdivision are given by the k+1 flags of simplices of S. So these are the chains of inclusions of simplices. And now there's a definition due to Sheehy. So if you have S as a simplicial complex, then you get a barycentric filtration, where the kth piece of it is the set of flags in the barycentric subdivision of S, where the minimum element has dimension greater than or equal to k-1. So, as k goes up, you see sort of higher and higher dimensional flags where they start anyway. And now to turn this into a bifiltration, if you have a finite metric space, you look at what we call the subdivision Rips filtration, where at k epsilon, this is the kth barycentric filtration of the epsilon scale Vietoris Rips complex. Okay, and if you can check that this is in fact the bifiltration. And now the theorem that we prove is that if x and y are finite metric spaces, then in analogy with the one-dimensional stability theorem, the homotopy interleaving distance between the subdivision Rips filtrations of x and y is bounded by the Gromov-Provorov distance between the metric measure spaces x and y. Now, the homotopy interleaving distance is some kind of distance on bifiltrations, and the Gromov-Provorov distance, it's a generalization of the Gromov-Hausdorff distance to metric measure spaces, where now you match your spaces and then you use the Provorov distance, which is a metric on measures. And you could replace this with some sort of optimal transport distance if you want. Their analogous theorems. So this is attractive or conceptually satisfying, but it has a practical problem. The subdivision Rips and the measure filtration bifiltrations are too big. You can't use them. So in practice, people instead use what's called the degree Rips bifiltration, where the idea is you filter Rips complexes by the degree of the vertices in the one skeleton. And for this, we also can prove stability results, but they're much weaker. And let me give you an example of what I mean by that. So if you look at, here's an example where, on the left, we have a densely sampled circle. On the right, we've added a bunch of noise points in the middle. And now if we use the degree Rips filtration and compute the multidimensional persistence of these things, and we use Ripser to do this, which is a software package due to Lesnick and Wright, what we get on the left is, this is a picture of the rank of the graph of the rank of the barcode. And if you look on the left, what you get is there's a big gray region where you detect that cycle. And the vertical axis is the epsilon, the feature scale, and the horizontal axis is the degree scale, the density scale. On the right, what you see is you get a much more truncated region of parameter space where you can see the cycle. Um, and it's sort of noisier around the edges. Um, and what the stability theorem guarantees is that that little black region is conserved between the two pictures. Um, and, that's not a very strong stability result. But what we can prove that generically speaking, this kind of stability result is tight. So what I want to leave you with is that, that we have these sort of probabilistic stability results in this context, but B, these, I think, raise as many questions as they answer. And in the sense that one thing you might want to know is what is going on with degree rips, right? This is an efficient and good bifiltration. It's clear in this example that there's more structure preserved, there's more stability than is captured by our result, even though our result is generically tight. And so maybe maybe this says you need a more refined stability theory, or maybe it says that the counterexamples are somehow exotic, and under sort of genericity hypotheses or something, you could expect a stronger result. I don't know, but it would be good to have something that talks about this. And the other thing to say is that I think that there's a real pressing need for bifiltrations that encode density and are parameter free in the way that these ones are, that are both tractable and have an attractive stability theory. And of course, these questions go together. But I think that in order for multidimensional persistence to live up to its potential in applications, we need more, we need more stability results, and we need filtrations that we can compute that have them. Anyway, that is what I wanted to tell you. So please read the paper or get in touch if you have questions about any of this work. Thanks so much.